Hidden 10 billion light-years away lies TON 618, a black hole so massive it defies imagination. Its gravity bends light-time and even our sense of reality. Tonight we'll explore the largest black hole ever known. If you enjoy these cosmic journeys, please like, subscribe, and share, and tell us in the comments, what do you think lies beyond the event horizon? Thank you for watching. Now let's begin. Across the expanse of the observable universe, an intricate web of matter stretches outward in every direction. It is neither uniform nor random, but arranged in vast, delicate filaments that thread through immense voids. Galaxies are not scattered evenly, but instead follow the quiet architecture of gravity's design, forming clusters that gather into greater superclusters, connected by strands of gas dust and dark matter. Between these glowing filaments lie enormous empty regions, some hundreds of millions of light-years wide, where only the faintest whisper of hydrogen drifts. This pattern, bright threads and deep hollows, is known as the cosmic web, a structure shaped by nearly 14 billion years of expansion and attraction. Within it, space itself expands while gravity works patiently to draw matter together, sculpting clusters where thousands of galaxies move through shared gravitational wells. In these immense gatherings, time flows calmly but relentlessly. Each cluster is an island of light suspended in the dark ocean of the cosmos, its galaxies rotating slowly around invisible centers of mass, guided by dark matter, halos that neither shine nor absorb, yet outweigh all visible stars combined. In the most massive regions, the balance between gravity and expansion creates a kind of still motion, everything in slow drift, too vast to seem active, yet always in quiet change. The light we see from these distances began its journey when the universe was young. Some of it has travelled for billions of years before reaching modern telescopes. This light, faint and stretched by the universe's expansion, carries stories of ancient galaxies forming, colliding and merging into larger systems. Astronomers can trace the cosmic web through its influence on this light, mapping the invisible matter that outlines its framework. Every bright dot, every smudge of distant glow sits somewhere upon these filaments, part of a structure that extends beyond the reach of sight or sound. TON 618 resides within this immensity. Though it appears as a single luminous point in deep surveys, it is in fact an entire galaxy, one that holds at its centre the largest known black hole. Yet even such an extraordinary object belongs to the quiet regularity of the cosmic pattern. Around it are other galaxies, some smaller, some larger, all bound within the same gravitational filaments that link across the universe. The forces that created TON 618's environment are the same that shaped every galaxy: gradual condensation of matter, merging of smaller systems, and the persistent pull of invisible mass guiding visible form. To imagine the scale of the setting, one must move outward rather than inward. From the black hole to the galaxy, from the galaxy to the cluster, and from the cluster to the network of superclusters, the view expands into something without edges. Light from neighbouring clusters takes hundreds of millions of years to cross the space between them, yet the structure holds steady because it evolves on timescales far longer than any human measurement. The largest filaments, stretching for more than 1 billion light-years, define the very shape of the universe at its grandest scale. Within them, galaxies form knots, denser regions where gravity collects matter from the surrounding cosmic web. These knots become clusters, and clusters merge into superclusters, producing concentrations of galaxies numbering in the tens of thousands. The region where TON 618 lies belongs to such a supercluster, one among countless others, yet remarkable for containing one of the most radiant quasars ever observed. In this vastness, silence prevails. The distances are too great for any sound to travel, and the energy of even the brightest galaxies diminishes to a faint shimmer against the cosmic background. Space itself curves gently around concentrations of mass, bending the path of light and shaping the way the universe appears to an observer billions of light-years away. The patterns we see today are ancient relics of fluctuations that began shortly after the Big Bang, amplified by gravity until the first stars ignited. These primordial ripples have grown into the filaments that define the large-scale structure now. Over time, galaxies within the web continue to evolve. Some draw closer and merge, forming elliptical systems. Others retain their spiral form, continuing to build stars slowly from the gas that remains. Black holes at their centers feed intermittently, growing each time matter falls inward. Ton 618's black hole once fed at a tremendous rate, illuminating the universe with its energy output visible across billions of light-years. That glow is what allows astronomers to detect it today, though the light that reaches Earth was emitted when the universe was less than half its current age. The cosmic web, though enormous, is tenuous. Most of its mass lies in invisible dark matter, and most of its volume contains nothing more than a few atoms per cubic meter. The glowing points of galaxies represent only a tiny fraction of all existence, yet they are the markers by which the structure becomes visible. In between, the intergalactic medium stretches thin and cold, heated only slightly by ultraviolet light from distant stars and quasars. The temperature of this space varies slowly, with time cooling as the universe expands. Within the filaments, however, gas is drawn inward, compressed by gravity and warmed as it flows toward galaxies like the one hosting Ton 618. From the perspective of deep time, the web's appearance changes slowly, like a faint pattern in water disturbed only by the gentlest of tides. Each galaxy moves through its filamentary lane, influenced by the pull of neighboring clusters. Collisions are rare but inevitable on long scales, giving rise to new structures. Over billions of years, these mergers build up the massive galaxies that populate the cores of clusters. The elliptical giant that holds Ton 618 is the product of such a history, born from countless collisions of smaller progenitors. But in the scale of the cosmic web, even this immense galaxy remains a mere point of light, one of uncounted billions tracing the geometry of the universe. The cosmic microwave background, faint radiation from the birth of the cosmos, fills the space between these structures. Its uniform glow provides the backdrop against which all galaxies shine. This background, nearly constant in every direction, reveals subtle variations that mark the seeds of the present-day web. From these minute differences, gravity has drawn together the matter that now forms galaxies, clusters, and superclusters. Ton 618 and its surroundings are one outcome of this ancient process, a single luminous node on a network that spans everything observable. As the universe continues to expand, the filaments lengthen and the voids widen. Distant galaxies drift farther apart, their light stretched into longer wavelengths. The large-scale structure remains, but over future eons it will thin and fade as expansion accelerates. Still, the cosmic web will persist as the enduring outline of matter's earliest movements. Within it, places like Ton 618 remind observers that even the most extreme objects are part of a tranquil and ordered design, shaped by the slow and constant laws of physics that govern all space. Within the cosmic web, clusters of galaxies gather into even greater formations known as superclusters. These structures represent the largest coherent assemblies bound at least partially by gravity, before cosmic expansion begins to pull them apart. A supercluster may span hundreds of millions of light-years, containing tens of thousands of galaxies, each glowing faintly among rivers of dark matter. These immense congregations resemble drifting continents of light, moving slowly through the dark sea of space. They are not permanent in the human sense, but evolve across billions of years as galaxies merge, fade, or move outward toward the edges of the gravitational domain. Within such a region lies the environment that hosts TON 618, embedded among countless other galaxies that share a common origin within the same filament of the cosmic web. The large-scale gravity that binds this region together acts gently but continuously, keeping the galaxies in a slow dance, whose steps are measured not in years but in epochs. The gas and dark matter distributed through a supercluster define its texture. Much of the visible matter is confined to galaxies, but the space between them is not empty. Thin streams of hot plasma connect one system to another, faintly visible in X-rays. These vast tendrils trace the invisible skeleton of dark matter beneath. Astronomers map these filaments by studying how their mass bends the light of more distant galaxies, a phenomenon called gravitational lensing. The slight distortions they measure reveal a pattern too large for any direct observation, confirming that every luminous structure sits within a web of unseen gravity. TON 618's home lies within one of these intricate networks, its position governed by the slow tug of nearby clusters and the overall pull of its supercluster. In these expanses, time flows with quiet indifference. Galaxies that appear close together in the sky may in truth be separated by hundreds of millions of light years, yet still belong to the same overarching structure. The motions are subtle, tiny shifts in velocity compared to the speeds of light. But given enough time, these gradual drifts sculpt the evolution of the entire region. Some clusters draw closer and merge, others are carried apart by cosmic expansion. The balance between attraction and expansion determines whether a region remains gravitationally bound or eventually disperses. In the case of the supercluster containing TON 618, gravity still dominates locally, keeping its components gently coalesced, even as the larger universe continues to stretch. Observing a supercluster is an act of looking deep into time. The light that leaves one of its distant members may take billions of years to reach an observer, so every image represents a past state. TON 618 itself, shining as a quasar, sends light that began its journey when the universe was less than half its current age. The photons reaching Earth today have crossed intergalactic distances through expanding space, stretched by the passage of time into longer wavelengths. What began as ultraviolet brilliance now arrives as visible or even infrared glow, a softened echo of an ancient outburst. This gentle dimming and red-shifting turn violence into calm, allowing the extreme energy of a quasar to appear as a faint, steady light when seen from so far away. Within the supercluster, galaxies differ widely in form and activity. Spiral galaxies continue forming stars, their disks bright with young blue clusters. Elliptical galaxies, larger and older, contain mostly red, long-lived stars and little new gas. In their centers, massive black holes rest, sometimes quiet, sometimes active, depending on the availability of infalling material. The galaxy that shelters TON 618 is of the giant elliptical type, vast and aged, likely built through a long sequence of mergers that stripped it of cold gas. Its central black hole, however, once had abundant fuel, and during that period of feeding it became one of the brightest beacons in the visible universe. The surrounding region is sparse yet intricate. Between galaxies, low-density gas forms a tenuous bridge linking systems together. The temperatures here can reach tens of millions of degrees, though the gas remains nearly transparent due to its thinness. Occasionally, two clusters within the same supercluster interact, compressing this intercluster gas and producing faint arcs of X-ray emission. These signs mark the slow interplay between gravity and expansion, the balance that holds the universe's largest structures in quiet tension. TON 618's environment is shaped by this same equilibrium, where inflowing matter from the cosmic web continually replenishes the mass of its host cluster, while expansion tugs gently outward. Over cosmic time, superclusters evolve. Some parts become more tightly bound, forming future massive clusters. Others drift beyond one another's reach as expansion accelerates. In distant epochs, many of today's superclusters will fragment into isolated islands of galaxies separated by ever-growing voids. TON 618's cluster will eventually stand alone in a darkening universe, its surrounding galaxies receding beyond visibility. Yet in the present cosmic era, these connections remain, allowing matter, light, and energy to move slowly through the filaments that define their shared domain. The presence of such a massive black hole at the center of one galaxy does not disturb the serenity of the supercluster. Its influence extends only a limited distance, confined to the scale of its host. Beyond that, gravity from the cluster as a whole dominates. The black hole's radiation, though luminous, dissipates across billions of light years until it becomes a faint signal within the background glow. The collective emission from all quasars, including TON 618, contributes only a small fraction to the total brightness of the sky. The rest comes from the ordinary light of stars and the diffuse glow of intergalactic gas. Astronomers studying superclusters often use redshift surveys to map their extent. By measuring how much the wavelength of light has stretched, they infer both distance and motion. Through these maps, the positions of galaxies form a vast three-dimensional lattice. TON 618 occupies one node within this map, a coordinate in both space and time. Its extraordinary luminosity makes it easier to trace, serving as a reference point for understanding how matter accumulates in the distant universe. The patterns revealed by such studies confirm that even the most luminous quasars obey the same underlying structure as all other galaxies. They do not stand apart but fit seamlessly into the grand architecture of cosmic evolution. On human scales, such distances and times defy ordinary comprehension, yet the physics that governs them remains simple gravity, pulling space, expanding light, travelling across emptiness. These steady processes combine to produce a universe that appears both dynamic and tranquil. Within the framework of the supercluster, each galaxy moves according to predictable laws, influenced by its neighbours but following the deeper rhythm of cosmic expansion. The result is a quiet, majestic order, where even the most immense events unfold gradually without haste. In this balance of scale and stillness, the home of TON 618 finds its place. It is neither the centre nor the edge of the universe, but one expression of its structure. Around it, clusters form, drift, and evolve repeating patterns seen everywhere else. The same forces that shape this region shape all others, ensuring continuity from the smallest galaxy group to the largest filament. TON 618's supercluster is thus not unique in form, but remarkable in what it contains: a single black hole of such vast mass that its light crossing time and distance reveals both the grandeur and the calm of the universe it inhabits. Among the immense structures of the supercluster lies a quieter and more familiar grouping known to astronomers through the constellation of Coma Berenices. It is here within this remote region of sky that the galaxy hosting TON 618 is located. The name Coma Berenices, drawn from ancient observation, refers to a modest patch of stars visible to the naked eye on a clear night. Yet behind those faint points stretches a concentration of galaxies beyond counting. Modern telescopes reveal them not as isolated bodies but as members of a dense cluster threaded with faint bridges of gas and dark matter. TON 618 sits far beyond the visible cluster itself, deep within the same general direction, in a realm where distance is measured in billions of light-years, and where each luminous spot in the field represents not a single star, but a galaxy containing billions of stars of its own. Observations of the region show a diversity of galactic forms, flattened spirals with winding arms, smooth ellipticals glowing softly, and irregular shapes that betray past collisions. The Coma Berenices area is part of a rich environment known as the Coma Supercluster, one of the nearest massive galaxy congregations to Earth. Within this setting, matter collects along strands that run through intergalactic space, and TON 618, though far more distant, belongs to a continuation of such a filament, a place where gravitational tides long ago brought enormous clouds of matter together. The perspective from our vantage point allows astronomers to look back across more than 10 billion years of cosmic history, seeing the universe as it once was when light first began its long journey from TON 618's galaxy. The light detected from this object appears faint to human eyes, but carries an intensity that at its source surpasses the brightness of entire clusters of galaxies. Through instruments capable of gathering light across different wavelengths, astronomers have learned that TON 618's emission peaks in ultraviolet and X-ray energy signatures of material falling toward a supermassive black hole. When translated to visible images, this radiation softens, turning extreme energy into delicate color gradients. The result is an appearance of serenity rather than violence, a calm blue-white glow suspended amid the darkness. The measured redshift of TON 618 corresponds to a time when the universe was roughly 5 billion years old, meaning that more than half of its history has unfolded since that light began its travel. Each photon that reaches a detector today carries information about the state of matter, temperature, and motion of that distant era. The Coma Berenices region serves as a cosmic reference point for understanding where TON 618 fits within the larger geometry of the universe. The galaxies visible nearby in the sky are in reality much closer separated by vast distances along the line of sight. Yet through this alignment, astronomers can compare local clusters with the more ancient quasar system, bridging different epochs of galactic evolution. The nearby Coma cluster, with its thousands of galaxies, offers a glimpse of what environments like TON 618's may have evolved into after billions of years. Massive elliptical galaxies dominate its core, surrounded by fainter gas-poor systems. Their light is redder, their activity quieter, suggesting an advanced stage of galactic life. By contrast, TON 618's host exists in a younger cosmic period, when fuel was still abundant and black holes could grow rapidly through steady accretion. This connection between distance and time forms the basis of observational cosmology. Looking outward is looking backward. The faint smudge of TON 618 represents an ancient event still unfolding across space preserved in light. The path of that light is shaped by gravity as it travels bent slightly, by the mass of galaxies and clusters along the way. Some of its photons have likely passed through filaments of gas that leave faint absorption lines in the spectrum, allowing researchers to study the matter that lies between galaxies. Each small dip in the spectrum corresponds to an intervening cloud, marking its distance and composition. In this way, TON 618 becomes not only an object of interest itself, but also a beacon for probing the universe it illuminates. The galaxies of the Coma Berenices region vary in brightness and shape, but most are members of groups drawn together by gravity into larger configurations. Some form pairs locked in mutual orbit. Others drift alone at the edges of the cluster. In visible light, they appear calm, but radio and X-ray observations reveal an active environment where plasma and magnetic fields interact. These signals trace the invisible processes of heating, cooling and motion that define the intergalactic medium. TON 618, far beyond this particular cluster, demonstrates these same phenomena on a grander scale, its radiation affecting the gas throughout its host galaxy, and even beyond heating and ionizing material over thousands of light years. The apparent stillness of such systems conceals ceaseless motion. Within each galaxy, stars revolve around a common center, completing orbits that take hundreds of millions of years. Clouds of gas drift inward and outward as gravitational tides shift. In the vast spaces between galaxies, dark matter forms the binding scaffold that holds everything in place. Though invisible, its presence is felt through the collective motions of galaxies and the curvature of the light that passes nearby. Without it, the Coma supercluster would not exist. Its galaxies would drift apart instead of forming the interconnected web observed today. TON 618's home follows the same pattern, resting within a deep gravitational potential, well carved by dark matter long before the first stars ignited within it. The scale of this environment stretches comprehension. From one end of the Coma supercluster to the other, light requires more than 300 million years to cross. Yet compared to the entire observable universe, even this vast realm is only a small fraction. The number of galaxies visible within such a region reaches into the tens of thousands, each composed of hundreds of billions of stars and each likely containing a black hole at its core. Amid this statistical enormity, TON 618 stands out not by its location but by its mass and luminosity. It represents an extreme case of a universal rule that nearly every galaxy hosts a central black hole whose properties reflect those of the surrounding stars. In TON 618, that relationship has reached a scale unmatched by any other measured example. As astronomers examine the Coma Berenices region across wavelengths from optical to radio to X-ray, they piece together a three-dimensional view of matter distribution. Computer simulations replicate these patterns, showing how gas flows along filaments toward nodes where galaxies merge. Such models confirm that systems like TON 618 arise naturally within this framework, forming where early density peaks attracted abundant matter. Over cosmic time, these concentrations grew into the titanic black holes now observed at great distances. The match between simulation and observation lends confidence that the same laws of gravity, hydrodynamics, and radiation govern both the nearby Coma cluster and the faraway quasar in the same direction. The light from TON 618 continues to travel indifferent to the eons that pass. As it does, the universe expands further, stretching the space through which it moves. Its wavelength lengthens, its energy diminishes, and its arrival marks one more photon in the constant drizzle of ancient information reaching Earth. In the sky, the region of Coma Berenices remains quiet and faint, yet within that faintness lies the memory of extraordinary events, the growth of galaxies, the birth of stars, and the awakening of the universe's largest black hole. Through calm observation and careful measurement, this distant corner of space reveals not drama, but continuity. The slow, steady unfolding of the cosmos from the structure of clusters to the invisible depths where gravity reigns unopposed. The galaxy that shelters TON 618 stands as one of the grandest known elliptical systems, a colossal structure of old stars, faint gas, and dark matter. Unlike the elegant spirals common in younger galaxies, its form is smooth and featureless, shaped by countless mergers over cosmic time. From afar it appears as a pale halo, its light diffused evenly in every direction, fading slowly into the surrounding darkness. The absence of defined arms or dust lanes reflects an advanced age. Most of its cold gas has long since been converted into stars or expelled into intergalactic space by ancient bursts of energy from the central core. What remains is a population of red and yellow stars, long-lived and steady, orbiting the galaxy's heart in quiet unison. Each star contributes a small share of the total radiance, and together they form a sphere of light several 100,000 light-years across, larger than the entire Milky Way. The gravitational field of such a galaxy is immense. Every star, every trace of gas, and every dark matter particle moves in response to its pull. The motion of these components can be inferred through shifts in their spectral lines, which show that stars closer to the centre orbit more swiftly than those in the outskirts. This gradient reveals the unseen mass that holds the system together, a vast reservoir of dark matter extending well beyond the visible boundary. Within this gravitational shell lies the region dominated by ordinary matter, a place where stellar orbits intersect, overlap, and blend into the smooth brightness observed through telescopes. The faint glow of the galaxy's outer halo reaches into intergalactic space, where stray stars and globular clusters drift in long, elliptical paths bound yet remote. The galaxy's history is written in its light. The uniform colour of its stars suggests that most formed in a short, intense period of activity billions of years ago. Afterward, smaller galaxies fell inward and were absorbed, adding mass but little new star formation. These mergers puffed up the structure, erasing traces of ordered rotation and leaving behind a pressure-supported sphere of random stellar motion. The process was gradual but relentless, turning a once spiral ancestor into the massive elliptical seen today. At its core, the accumulated debris of past galaxies surrounds the supermassive black hole, which once shone as a quasar. Even though the galaxy now appears dormant in visible light, the memory of that active phase remains in the hot gas filling its centre, and in the extended radio lobes left behind by ancient jets. Astronomers study such galaxies to understand the final stages of galactic evolution. Ellipticals, like the host of TON 618, represent the end points of growth, where gas is scarce and star formation has ceased. Their smoothness and symmetry arise from the mixing of stellar populations over billions of years. In this state, energy flows primarily from the slow aging of stars and from the residual heat of the interstellar medium, not from the creation of new ones. Occasionally, small infalling systems bring fresh material, triggering brief flares of activity, but overall the galaxy remains calm, radiating steadily, without sudden changes in brightness. The host of TON 618, however, distinguishes itself by the magnitude of its core. The black hole at its centre outweighs the combined mass of several galaxies, altering the dynamics even far beyond the nucleus. Within thousands of light years, the orbits of stars are influenced by its gravity, shaping a steep central brightness profile known as a cusp. Observations of similar systems show that such features develop through repeated mergers of black holes during galactic collisions. Each event emits gravitational waves and reshapes the core, eventually leaving behind a single dominant object. TON 618's central mass indicates a long chain of such mergers accumulated across cosmic epochs. Its current quiescence does not diminish its significance. Rather, it marks a period of rest in a history punctuated by extreme energy release. The gas that remains within the galaxy is thin and hot detectable, mainly through X-rays. It forms an extended atmosphere around the central region, kept warm by past outbursts from the quasar and by the slow infell of material from the halo. The temperature of this gas reaches tens of millions of degrees, yet its density is so low that it would seem like a vacuum to any physical probe. Over time, some of it cools and settles toward the core, feeding the black hole in faint, continuous streams. This quiet accretion ensures that the central engine never truly turns off, but flickers gently at levels too low to outshine the host. The balance between heating and cooling maintains a steady equilibrium, preventing new stars from forming while preserving the stability of the galaxy's structure. Surrounding the luminous body of the galaxy is a diffuse halo populated by globular clusters, dense spheres of ancient stars that orbit like small satellites. These clusters trace the mass distribution and reveal the shape of the galaxy's gravitational field. Their motions, when measured precisely, confirm that dark matter extends far beyond the visible light binding the system within an invisible framework. Beyond the halo, faint streams of stars mark the remnants of disrupted dwarf galaxies stretched into long arcs by tidal forces. These relics tell of a past filled with encounters and absorptions, a quiet record of growth through cosmic time. The radiation from the galaxy's stellar population gives it a golden hue, dominated by cool-aged stars near the end of their lifespans. Many a red giant, swollen and luminous, nearing the stage where they will shed their outer layers and leave behind compact white dwarfs. Their collective light provides a steady glow constant across millions of years. Through this glow, astronomers can estimate the age of the system, placing its formation soon after the universe's most active era of starbirth. The lack of blue light indicates that the youngest massive stars, which live only a few million years, have long vanished. What remains is a mature, stable assembly of stellar remnants and long-lived suns burning at a measured pace. Compared with more turbulent galaxies, this elliptical appears almost timeless. Its rotational energy has long since dissipated, leaving random motion as the main form of internal balance. This lack of rotation prevents the formation of spiral arms and keeps dust from settling into disks. The galaxy is instead a slow ocean of stars, each moving independently yet confined by the collective gravity of all. Near the center, the pull becomes stronger, velocities higher, and the transition toward the domain of the black hole begins. The light there brightens subtly, forming a core that merges almost seamlessly with the surrounding glow. Only through spectroscopy can observers discern the increase in velocity dispersion that betrays the gravitational presence of something extraordinary. The host galaxy of TON 618 embodies both the quiet and the power of cosmic evolution. It no longer forms stars in great numbers, nor does it radiate violently as in its quasar phase, yet within its calm structure lies the memory of all those transformations. Every photon leaving its stars or gas clouds tells a part of that long story of mergers heating and gradual settling into equilibrium. Against the background of the Coma Berenices region, this galaxy stands as an immense soft sphere of light, its surface brightness declining smoothly into blackness. Inside, unseen but dominant, the largest known black hole waits at the center, marking the next inward step of the journey through TON 618's layered universe. At the heart of the immense elliptical galaxy that holds TON 618, light intensifies again. The faint golden radiance of old stars gives way to a concentrated brightness that overwhelms everything around it. Here lies the galactic core, a compact region, only a few light years across, yet responsible for a glow that outshines the rest of the galaxy combined. This luminosity does not come from stars but from matter, falling toward the central black hole, compressed and heated to extraordinary temperatures. The result is a quasar or quasi-stellar object, a beacon visible across billions of light years. In this state, the galaxy becomes one of the most radiant objects in the known universe, its energy output exceeding that of hundreds of trillions of suns. For astronomers observing from Earth, the quasar phase represents a rare window into processes otherwise hidden by darkness. The light emitted here was produced long ago when the universe was still young and active, and it carries with it the record of matter spiraling into the most extreme gravitational well yet measured. In the dense environment near the core, the interstellar medium transforms. Ordinary gas and dust drawn inward by gravity encounter shock fronts and magnetic turbulence. Collisions among particles generate intense heat, producing radiation across the electromagnetic spectrum from radio waves to gamma rays. The central region glows in ultraviolet and X-rays while surrounding zones emit visible light and infrared. The combination forms the characteristic spectrum of a quasar, a blend of lines broadened by high-velocity motion. These spectral features allow scientists to determine both the composition of the gas and the speed at which it moves, often approaching significant fractions of light's velocity. The patterns observed in TON 618 reveal turbulent flows and extreme energy densities, confirming that its central engine once accreted material at or near the theoretical limit imposed by radiation pressure. Despite this immense power, the quasar's radiation spreads through space, quietly diffused over great distances. From billions of light-years away, it appears as a single, steady point of light, no larger than a star, though its true scale dwarfs entire galaxies. The stability of that light, sustained for millions of years, indicates a steady inflow of matter during its active phase. Gas from the surrounding galaxy, channeled by gravitational interactions and remnants of mergers, funneled toward the center in vast streams. As this material spiraled inward, angular momentum forced it into a disk-like structure, flattening under rotation and heating through friction. Closer to the black hole, temperatures rose until the gas emitted blinding radiation, turning potential energy into observable light. This mechanism explains the prodigious brightness of quasar's gravity, converting mass directly into energy, with efficiencies far exceeding nuclear fusion. The galactic core housing, TON 618, would have been a region of immense contrast. Beyond the luminous nucleus, the surrounding space was filled with warm gas and old stars, their combined gravity anchoring the system. Closer to the quasar, radiation pressure created winds that pushed outward, sculpting the interstellar medium into complex shapes. Some of this material escaped entirely, enriching the galaxy's halo with heavy elements. Other portions cooled and condensed into clouds that later formed new stars, briefly renewing activity before the gas supply dwindled. Over cosmic time, the central black hole's energy output regulated the galaxy's evolution, preventing unchecked star formation and maintaining thermal balance. The energy released by TON 618's quasar can be visualized as concentric regions of influence. The innermost area, a few light days wide, radiates fiercely its brightness, varying slightly as accretion fluctuates. Surrounding it is the broad line region, a zone of gas clouds moving at thousands of kilometers per second, illuminated by the central source. Farther out lies the narrow line region, where slower moving gas emits distinct spectral features. Together, these components produce the signature quasar spectrum observed through telescopes. The light from these layers carries information about velocity, temperature, and density, allowing astronomers to construct models of the system despite its enormous distance. For TON 618, such analyses suggest a black hole mass of many tens of billions of solar masses, making it the largest reliably measured to date. The quasar's radiation interacts with everything it touches. Photons traveling outward ionize atoms, strip electrons from gas, and generate faint halos that can extend for tens of thousands of light years. At the same time, dust grains absorb and re-emit energy in infrared, producing a glow that reveals the total power output. Observations across different wavelengths confirm that TON 618's quasar once radiated near the theoretical limit of luminosity known as the Eddington limit, where outward radiation balances inward gravitational pull. This equilibrium allows accretion to continue efficiently without blowing away the surrounding material. Over time, as the fuel supply decreases, the brightness subsides, leaving behind the dormant state seen in many modern galaxies. The light escaping from Ton 618's core began its journey when life on Earth did not yet exist. It travelled through expanding space stretched by the growth of the universe. Each wave of energy that arrives now carries with it the imprint of an earlier cosmos, hotter, denser, and younger. The photons we detect represent a small fraction of the total emitted, yet even this diminished glow allows scientists to study conditions billions of years in the past. Through precise measurement of its redshift and luminosity, Ton 618 serves as a reference point for understanding how black holes and galaxies co-evolve. Its extreme properties anchor models of cosmic structure formation, showing that the seeds of immense systems were already present early in the universe's history. The quiet brightness observed from Earth belies the intensity within the quasar itself. In the region near the event horizon, gravity accelerates matter to near light speed. Magnetic fields twist into loops and arcs, channeling some of the energy into jets that extend beyond the galaxy. These jets, though not yet described in detail at this stage of exploration, mark the outer limits of the quasar's influence. Their radiation interacts with intergalactic gas heating and ionizing material across vast distances. The combined effect is to link the fate of the black hole with that of its host galaxy, and even the larger environment of the cluster. Over millions of years, the activity of Ton 618's core would have fluctuated, governed by variations in available fuel. Periods of intense accretion alternated with quieter intervals when the disk thinned and cooled. Each cycle left subtle marks on the surrounding gas shock waves, chemical enrichment and shifts in pressure that shape the galaxy's evolution. Today, the light that reaches observers is the integrated record of those countless fluctuations averaged into a calm, steady glow by the immensity of distance. From such serenity, astronomers infer not absence of activity, but a balance between creation and destruction maintained over cosmic time. The central quasar of Ton 618 demonstrates the universe's ability to transform gravity into radiance, without noise or motion visible to human senses. What appears tranquil from afar is in reality a continuous exchange of mass and energy occurring at unimaginable scales. Within this luminous heart, the line between stability and collapse narrows to fractions of a second, yet the overall result remains smooth and enduring. The galaxy that hosts it drifts quietly through the supercluster, its ancient stars circling an invisible center that once blazed with the brightness of creation itself. Beyond the brilliant center of Ton 618's galaxy lies an environment that bridges the scale between the galactic interior and the broader cosmic medium, the region through which gas dust and radiation flow inward and outward in a steady exchange. This zone, vast yet delicate, forms the surrounding atmosphere of the quasar, linking the black hole's immediate environment to the intergalactic web. The intergalactic medium itself is an enormous reservoir of tenuous gas that occupies the space between galaxies, filling the filaments of the cosmic web with hydrogen, helium, and trace elements produced by earlier generations of stars. Though incredibly thin, often containing only a few atoms per cubic meter, it holds more total mass than all the stars in the universe combined. Through it, matter migrates slowly toward denser regions drawn by the persistent pull of gravity. Ton 618's host galaxy sits at one of these intersections where the intergalactic medium flows gently inward along filaments feeding the system over billions of years. The process is not dramatic. Streams of gas drift through dark space, almost imperceptibly guided by gradients in density and temperature. Some of this material never reaches the galaxy. Ultraviolet radiation from quasars and galaxies keeps much of it ionized, preventing collapse. Yet a fraction cools as it travels, losing energy until it condenses enough to fall inward. When this happens, the gas accelerates, gradually following the gravitational contours that extend far beyond the visible boundary of the host galaxy. This steady inflow represents one of the fundamental mechanisms by which galaxies grow and maintain activity, a quiet circulation of matter between the intergalactic medium and the dense regions within. Around TON 618, this accretion occurs on a monumental scale. The quasar's past luminosity suggests that vast quantities of material once streamed inward from surrounding space. Numerical simulations show that such flows can persist for billions of years, creating cold filamentary streams that penetrate the hot galactic halo and reach the central regions almost directly. These filaments deliver gas rich in primordial hydrogen and helium, along with heavier elements recycled from past generations of stars. The slow, constant arrival of this material provides the raw fuel for both star formation and black hole growth. In the early universe, when TON 618 was young, these inflows would have been stronger sustained by higher densities and frequent mergers. Over time, as the universe expanded and cooled, the flow weakened but never ceased entirely. The gas entering the galaxy interacts with its surroundings in complex ways. As it meets the hot halo left by past quasar outbursts, it shocks and heats, radiating energy in X-rays. Some of it cools again, forming clouds that descend toward the inner regions. Some disperses, adding to the diffuse atmosphere. This interplay maintains a long-term equilibrium. Even as the black hole and stars consume matter, new material from the cosmic web replenishes what is lost, keeping the galaxy's evolution continuous. The temperature, density, and velocity of this gas can be inferred through absorption lines, imprinted on the light from the quasar itself. Each element leaves a unique fingerprint, allowing astronomers to map the conditions in space between the quasar and the observer. The light of TON 618 thus acts as a probe of the medium through which it travels, revealing not only the nature of the source, but also the vast invisible ocean that surrounds it. In this environment, radiation from the quasar plays a dual role. It illuminates the gas, making it visible through fluorescence, but also ionizes it, preventing further cooling. This feedback limits how much material can accumulate near the core at any given time. The balance between inflow and radiation defines the duration of quasar activity. Too much radiation pressure would expel gas outward, shutting down accretion. Too little would allow excessive inflow, leading to rapid but brief outbursts. TON 618's enormous mass indicates that it achieved this balance repeatedly across cosmic history, sustaining high accretion rates without exhausting its fuel supply too quickly. The energy released during these episodes not only affected the host galaxy, but also propagated outward, altering the state of the intergalactic medium over millions of light years. The light from TON 618 reveals evidence of these interactions. Absorption systems seen along the line of sight correspond to intervening clouds of gas at various redshifts, marking the distribution of matter across the universe. Some of these absorbers belong to the galaxy's own halo, while others lie far beyond, tracing the filaments that connect galaxies together. The pattern of their velocities shows that the intergalactic medium is not static, but flows continuously, influenced by the gravitational potential of massive structures. In regions near quasars, the gas tends to be hotter and more ionized, forming extended bubbles of high-energy plasma. TON 618, with its exceptional brightness, likely produced one of the largest such ionized zones ever created, a sphere of altered space, where radiation dominated the physical state of matter for hundreds of millions of years. The inflowing gas that reaches the galaxy's inner halo carries angular momentum that shapes its motion. Rather than plunging directly toward the center, it spirals inward, forming large-scale structures such as warped disks and tidal streams. These patterns evolve slowly, governed by turbulence and magnetic forces. Within these flows, pockets of denser gas can cool and collapse into stars, contributing to intermittent star formation, even in galaxies considered old and quiescent. Observations of distant quasars suggest that star formation and black hole growth often occur together, each process influencing the other through the shared supply of gas. TON 618's host would have followed this same cycle: inflow, ignition, feedback and renewal, all unfolding over timescales that span hundreds of millions of years. The intergalactic medium itself is far from uniform. It contains regions of varying temperature and density, some cold and neutral, others hot and ionized. Shocks from structure formation heat large volumes of gas to millions of degrees, producing faint X-ray emission, detectable only with sensitive instruments. Magnetic fields thread through this space, weak but pervasive, guiding charged particles and shaping the morphology of filaments. In simulations, these magnetic fields twist and stretch as matter flows along the cosmic web, forming patterns reminiscent of slow-moving currents in water. TON 618's galaxy sits within one of these currents, drawing matter from its surroundings even as it releases energy outward through radiation and jets. Across cosmic time, the gradual accretion of gas from the intergalactic medium determines the fate of galaxies. Those with steady inflow remain luminous and active. Those cut off from supply fade into quiet ellipses. TON 618's continued enormity implies a long history of successful feeding, maintained by its position within a dense filament of the cosmic web. Even now, though its quasar phase has likely subsided, the surrounding environment still holds enough gas to sustain low-level activity for billions of years more. The motions are too slow to be seen, but the process continues invisibly, a perpetual exchange between emptiness and matter. In the larger perspective, this flow of gas from intergalactic space into galaxies represents one of the fundamental engines of cosmic evolution. It ensures that the universe never becomes static, that even the most distant systems remain connected by invisible streams of material and energy. TON 618 is both participant and witness in this endless cycle. Its light crossing the vastness of space carries the signature of that connection, a reminder that every luminous point in the night sky, however solitary it appears, is bound to the rest of the cosmos by the same quiet, enduring flow. Deeper within the structure surrounding TON 618, the flow of matter becomes more concentrated, transitioning from diffuse galactic gas into dense rotating formations that mark the first stages of accretion. Here, within a few hundred light-years of the black hole, gravity organizes material into a flattened configuration shaped by angular momentum and friction. The gas and dust entering this region no longer drift aimlessly through interstellar space. They form ordered spirals, accelerating as they move inward, their paths tightening like the coils of a vast invisible whirlpool. The outer accretion structures of TON 618 exist in this zone, a region where the galaxy's internal gravity yields to the dominance of the central mass, and where radiation and motion merge into a complex balance. The outer accretion structures are not a single disk, but a hierarchy of layers. At their larger scales lie the remnants of tidal inflows and streams fragments of interstellar clouds that have been stretched by gravity into filaments. These gradually lose momentum through collisions and magnetic drag, settling into a flattened disk several light years across. Within this disk, gas temperatures rise as friction converts kinetic energy into heat. As particles interact, they release photons and the disk begins to glow faintly, its outer edge radiating in infrared and optical wavelengths. From afar, this emission forms a soft halo of light around the quasar, blending seamlessly with the galaxy's inner glow. Though faint compared to the core, it represents the first visible sign of accretion matter surrendering to gravity's pull. Closer inward, turbulence increases. Magnetic fields thread through the rotating gas-generating shear that transfers angular momentum outward. This process allows material to drift slowly toward the black hole while maintaining the overall stability of the disk. The balance between inflow and outward transport is delicate. If viscosity were too low, accretion would stall. If too high, the disk would collapse under its own instability. In TON 618, the enormous scale and energy ensure a steady state where inflow proceeds gradually, maintaining high luminosity over long periods. The density of the outer disk remains low enough for transparency, allowing radiation from the inner regions to pass through and heat it further. The temperature gradient across these layers spans thousands of degrees, increasing steadily toward the center. Surrounding the disk is the broadline region, a zone of gas clouds orbiting at thousands of kilometers per second. These clouds, illuminated by the quasar's intense radiation, emit characteristic spectral lines that appear broadened by their velocity. The broadening provides a natural measure of the black hole's mass. The faster the motion, the deeper the gravitational potential. Observations of TON 618 show extremely wide lines indicating orbital speeds so high that only an object of extraordinary mass could produce them. Each cloud represents a small parcel of material temporarily suspended between inward pull and outward pressure, glowing for a time before dispersing or falling inward. The combined effect is a luminous envelope that surrounds the disk, bright yet diffuse, contributing significantly to the quasar's visible light. Beyond these illuminated regions lies a zone of dusty gas, dense enough to obscure some wavelengths. This torus-like structure absorbs ultraviolet radiation from the inner disk and re-emits it in infrared, creating a secondary glow observable by specialized instruments. The existence of such dust suggests that even in extreme environments, solid grains can survive at certain distances from the central heat source. Their presence regulates the radiation field, absorbing bursts of energy and smoothing fluctuations. In the case of TON 618, the scale of this dusty envelope may extend for tens of light years, forming a cocoon around the inner accretion regions. Through this layer, much of the quasar's energy escapes, filtered into longer wavelengths by the surrounding material. The motion within these zones follows predictable patterns described by general relativity and plasma physics. Gas in the outer regions orbits nearly in accordance with Newtonian gravity, while closer to the center, relativistic effects begin to dominate. The orbits become increasingly elliptical, time dilation grows measurable, and the emission from the gas becomes blue-shifted on the side, approaching the observer, and red-shifted on the side, receding. These subtle asymmetries are seen in high-resolution spectra, and confirm that the disk of TON 618 behaves as predicted for material orbiting near a massive black hole. The gradual change in light across the disk's surface provides one of the few ways to study conditions that cannot be reached directly. The stability of the outer accretion structures depends on a continuous supply of matter from larger scales. Without replenishment, the disk would thin and fade as material either accreted inward or was expelled by radiation pressure. In TON 618's galaxy, this supply is maintained by the inflows from the interstellar medium and the intergalactic filaments described earlier. As long as the balance holds, the disk persists, converting gravitational energy into radiation with quiet efficiency. When the supply fluctuates, brightness changes follow, though these occur over long intervals, centuries or millennia, making them invisible on human timescales. The impression of steady light seen from Earth is thus a reflection of the immense scale over which the system operates. Within the broadline region, radiation pressure and gravity compete for control. Gas too close to the black hole becomes unstable and falls inward, while gas slightly farther out achieves temporary equilibrium. The dynamics here are chaotic, with clouds forming, dispersing and reforming in a continuous cycle. Despite this turbulence, the system as a whole maintains balance as local instabilities average out across vast numbers of particles. The radiation from these clouds is responsible for much of the quasar's spectral complexity, carrying information about velocity fields, temperature and ionization state. In TON 618, these lines appear unusually luminous, consistent with the enormous energy radiating from the inner accretion disk. The overall appearance of this region, if it could be observed directly, would resemble a nested sequence of glowing rings fading gradually into darkness. The outermost layers emit faintly in the infrared, the inner zones shine in optical and ultraviolet, and the innermost parts radiate in X-rays. All these emissions combine to form the quasar's composite spectrum. In this way, TON 618 transforms the simple process of gravitational infall into a vast multicolored beacon that illuminates the universe across billions of light years. Yet the process itself is remarkably smooth, following physical laws that remain constant from the smallest black holes to the largest. The outer accretion structures also serve as a mediator between the galaxy and the quasar, controlling how energy and momentum are exchanged. Outflows driven by radiation or magnetic forces carry mass away, forming winds that enrich the galaxy's halo with heavy elements. These winds, though faint compared to the central radiation, play a crucial role in galactic evolution, distributing material that will later form new stars or planets in distant regions. In TON 618, given its scale, such winds would have reached far into intergalactic space, affecting the thermal balance of nearby gas clouds. Even now, long after the peak of its activity, the imprint of those outflows may persist as subtle distortions in the surrounding medium. The outer accretion structures thus represent both the gateway and the boundary of the black hole's domain. They are where ordinary matter begins to transform, where cold gas becomes ionized plasma, where motion becomes heat, and where gravity's pull begins to dominate every other force. In the story of TON 618, this zone marks the transition from the galactic environment to the immediate sphere of the black hole, a calm but inexorable threshold, beyond which space-time and energy take on their most extreme forms. Moving further inward toward the heart of TON 618, the outer disk and its luminous clouds give way to the inner accretion zone, where gravity compresses matter into a dense, rapidly spinning structure only a few light days across. Here the temperature rises to levels that exceed millions of degrees, and the energy released per particle becomes higher than that produced by any stellar process. The accretion disk in this region is the true engine of the quasar, a continuous cascade of matter spiraling toward annihilation. It glows not from combustion or fusion, but from friction and gravitational conversion, turning the potential energy of infall into radiation. Every fragment of gas entering this realm experiences forces that stretch and heat it until atoms lose their electrons, creating plasma that radiates in ultraviolet and X-rays. For TON 618, this inner disk is immense by human standards, yet it occupies only a minute fraction of the galaxy, an incandescent whirlpool suspended in darkness, invisible to the eye, but detectable through its radiance across the cosmos. The structure of the disk is governed by fundamental physics. At larger radii, the gas remains relatively cool and opaque, its light reprocessed through layers of dust and plasma. Closer to the black hole, the disk becomes thinner, denser, and more luminous. The balance between gravitational attraction, pressure support, and rotational velocity defines its thickness, producing a geometry that depends on both the rate of accretion and the spin of the black hole. In TON 618, these factors combine to create a stable luminous disk that persists for millions of years. Each particle orbiting near the center moves at a significant fraction of the speed of light, tracing a nearly circular path that gradually decays as energy is lost through radiation. The energy released by this process is immense. A few % of the rest mass of the infalling matter is converted into light, a level of efficiency far beyond that of any stellar mechanism. The color and brightness of the disk vary with radius. The outer regions glow in visible light, the middle regions in ultraviolet, and the innermost zone in X-rays. Together they form a continuous spectrum that peaks in the high-energy bands. This smooth distribution allows astronomers to infer the temperature gradient across the disk, which in the case of TON 618 ranges from thousands of degrees near the outer edge to tens of millions near the inner boundary. The light escaping from these regions is not emitted uniformly. Due to the extreme velocity of the orbiting plasma, relativistic effects cause one side of the disk to appear slightly brighter as it moves toward the observer and dimmer as it recedes. This asymmetry, known as relativistic beaming, has been observed in the light curves of many quasars and serves as direct evidence for the rapid rotation of their accretion disks. Near the center, where gravity's pull becomes overwhelming, time itself slows relative to the distant universe. From an external perspective, the motion of gas appears to decelerate as it approaches the black hole, though locally it continues to accelerate. The inner edge of the disk marks the innermost stable circular orbit, the last region where matter can orbit without plunging inward. Inside this boundary, no stable paths exist, and the gas falls freely toward the event horizon. For a black hole as massive as TON 618, this inner radius may extend for billions of kilometers, yet in proportion to its scale, it is an extraordinarily compact region. The energy released here accounts for most of the quasar's brilliance, producing radiation so intense that it ionizes everything nearby. Above the disk lies a zone known as the corona, a tenuous cloud of high-energy electrons that scatters photons into even higher frequencies. The origin of this corona is still a subject of research, but it's thought to arise from magnetic reconnection and turbulence within the disk. The X-rays emitted from this layer interact with the cooler gas below, producing reflections and emission lines that reveal the geometry of the inner regions. In TON 618, the strength of this X-ray emission implies a powerful and dynamic corona capable of shaping the radiation spectrum observed from Earth. These interactions between disk and corona create a feedback loop, maintaining the thermal and magnetic balance necessary for stable accretion. The radiation escaping from the inner disk travels outward, passing through layers of plasma that modify its spectrum. Some of the energy is absorbed and re-emitted at longer wavelengths, while some escapes directly into space. The interplay between absorption, scattering, and emission produces the characteristic quasar continuum, a smooth blend of light spanning many orders of magnitude in energy. The consistency of this spectrum across quasars suggests that despite their size differences, the underlying processes are universal. TON 618 exemplifies this universality at its extreme limit, demonstrating how the same physical laws that govern small stellar black holes can operate on scales billions of times larger. The forces acting within the inner disk are among the most extreme known in nature. Gravity compresses matter to densities beyond any planetary or stellar comparison, while friction and magnetism stir it into constant motion. The magnetic fields generated by the rotation of charged plasma act like invisible threads that twist and reconnect, releasing bursts of energy that heat the corona and drive outflows. These magnetic interactions may also play a role in the formation of relativistic jets, though those structures extend far beyond the disk and belong to the next phase of this inward journey. For now, within the confines of the disk, they maintain the flow of angular momentum, ensuring that matter continues its slow spiral toward the center. From the standpoint of observation, the inner accretion disk of TON 618 represents a paradox: intensely active, yet perceived as tranquil. Its changes occur over timescales too long to observe directly, its brightness steady across human lifetimes. The variations that do occur are smoothed by the sheer volume of material involved. The result is a luminous steadiness, a cosmic constancy powered by relentless infall. Light from this disk has travelled across space for more than 10 billion years, stretched by cosmic expansion, but still carrying the imprint of conditions near the event horizon. Through this light, astronomers can reconstruct the environment of the most powerful engines in the universe, witnessing through radiation what cannot be seen by eye. The transformation of gravitational energy into light at TON 618's core is an efficient yet quiet process, one that requires no explosional violence, only the continual motion of matter obeying natural law. Each photon that escapes carries away a fragment of mass radiated into the universe as part of the ongoing cycle of energy. Over billions of years, this mechanism has allowed the black hole to grow, feeding on the material provided by its host galaxy, while simultaneously returning energy to space. The balance between creation and consumption defines not only the fate of TON 618, but also the equilibrium of countless other galaxies throughout cosmic history. In the quiet center of the galaxy, invisible behind clouds of plasma and light, the black hole continues its silent work. The accretion disk encircling it acts as both fuel reservoir and beacon, a spinning ring of incandescent matter that translates the pull of gravity into the calm glow seen across the cosmos. To distant observers, this radiance is steady, constant and serene, an enduring reminder that even in the most extreme corners of the universe, order persists and the laws of physics unfold with unwavering precision. Above the luminous disk of TON 618, suspended in the void like an invisible veil, exists a region of intense energy known as the corona. This zone, though tenuous and nearly transparent, is composed of highly energetic electrons, accelerated by magnetic turbulence within the accretion flow. The corona envelopes the inner disk like a halo of heat, scattering photons upward and outward, converting lower energy ultraviolet light into X-rays. Through this interaction, the corona becomes one of the most important yet least understood components of the quasar environment. It links the mechanical motion of infalling gas to the radiant output observed across vast cosmic distances. In TON 618, whose mass dwarfs that of any known black hole, this corona would extend across billions of kilometers, radiating energy equal to entire galaxies, while maintaining a near-perfect steadiness over immense spans of time. The origin of such a corona lies in the magnetic fields that arise naturally within the rotating plasma of the accretion disk. As charged particles move through the magnetic field lines, they twist and shear, storing energy in tangled configurations. When these field lines reconnect, the stored magnetic energy is released suddenly, as heat accelerating electrons to relativistic speeds. This process mirrors what occurs above the surfaces of stars like the Sun, though on scales magnified beyond comprehension. Each event injects fresh energy into the corona, maintaining its high temperature and constant emission. The X-rays produced in these interactions strike the surface of the accretion disk below, where they are absorbed and re-emitted as secondary light. This reflection produces characteristic spectral signatures, narrow iron lines and soft excesses in the spectrum that allow astronomers to infer the presence and structure of the corona even when it cannot be seen directly. The temperature of the corona may reach hundreds of billions of degrees, though density remains extremely low. Despite its heat, it emits no visible light, only high-energy photons. These photons interact with the disk through a process called Compton scattering, where they collide with electrons and exchange energy, modifying the spectrum of radiation that escapes into space. The resulting X-ray continuum carries information about the geometry of the system, revealing whether the corona is a compact sphere hovering above the black hole or an extended layer that drapes across the disk's surface. In TON 618, the enormous luminosity and smoothness of the observed radiation suggest a stable extended configuration, sustained by the black hole's extreme gravitational and magnetic environment. The corona's role extends beyond simple radiation. It participates in the regulation of accretion itself. By heating the upper layers of the disk, it affects the flow of material inward, influencing where and how energy is released. Some of the corona's high-energy particles escape entirely, forming the seeds of relativistic jets that extend along the black hole's rotational axis. Others deposit energy back into the disk, maintaining a balance that prevents runaway collapse or overproduction of radiation. The interaction between disk corona and jet forms a self-sustaining feedback loop, one that converts the simple act of falling matter into a complex symphony of electromagnetic processes. In the environment of TON 618, this system operates with precision born of scale. The gravitational field is so strong that even small disturbances are quickly smoothed out. Waves and instabilities that might disrupt smaller black holes dissipate here before they can propagate. The corona's stability over millions of years ensures that the quasar's luminosity remains nearly constant, providing a continuous beacon across cosmic distances. For astronomers, this steadiness is invaluable. It allows the light from TON 618 to serve as a reference for measuring cosmic expansion, for studying the absorption properties of intergalactic gas, and for testing theories of how energy behaves near the limits of physical law. Observing the corona directly remains beyond the reach of any telescope, but its fingerprints are unmistakable. When X-rays emitted by the corona strike, the inner disk's some are deflected by the immense gravity of the black hole, creating time delays and distortions in the observed signal. By measuring these echoes, scientists can estimate the size and shape of the corona and even detect relativistic effects such as gravitational redshift. The data gathered from quasars like TON 618 reveal that these features behave exactly as predicted by Einstein's general relativity, confirming that even under the universe's most extreme conditions, the fundamental laws hold true. The radiation produced by the corona interacts with matter far beyond the immediate vicinity of the black hole. X-rays and gamma rays streaming outward ionize gas clouds thousands of light-years away, altering their chemistry and structure. Some of this radiation escapes the galaxy, entirely influencing the temperature of intergalactic space. TON 618's corona operating over millions of years would have contributed to heating the cosmic medium around it, forming a faint yet measurable bubble of elevated energy. Within that sphere, atoms behave differently. Electrons stripped away and recombined in cycles that continue long after the quasar's peak activity fades. In this way, the corona acts as both a local and cosmic phenomenon, shaping environments far beyond its visible reach. The magnetic fields responsible for the corona's existence also give rise to ordered structures along the rotational axis of the black hole. When field lines anchored in the disk and corona twist together, they can channel energy outward in narrow beams, forming relativistic jets that extend for thousands or even millions of light years. Though these jets belong to a later stage in the inward journey, their connection to the corona is essential. The same magnetic processes that heat the corona also extract rotational energy from the black hole, launching particles into space at near light speed. The corona thus stands at the crossroads between the inward fall of matter and the outward flow of energy, mediating the conversion from gravitational collapse to cosmic radiation. Within TON 6018's corona space and time behaves subtly differently from ordinary intuition. Light emitted from near the black hole experiences gravitational redshift, losing energy as it climbs out of the deep gravitational well. To a distant observer, this results in a softening of the spectrum and a delay in the apparent motion of features near the core. The corona itself may appear slightly distorted, its light curved by the black hole's gravity, forming a lens-like halo around the invisible center. In some quasars, this bending produces rings or arcs when observed at high resolution. Though TON 618 lies too far for such detail to be resolved, the principles remain the same. Light bends, time dilates, and the geometry of space becomes an active participant in the structure of radiation. The stability of TON 618's corona represents one of the great equilibria in nature, a system where the most violent forces achieve perfect calm through balance. Gravity draws matter inward, magnetic fields lift energy outward, and radiation streams freely into space, carrying away heat while leaving the structure intact. Over millions of years, this equilibrium persists, a silent interplay between chaos and order. To observers billions of light-years away, the result is a steady glow of X-rays, a quiet pulse of the universe's most powerful mechanism. It is not noise but constancy that defines this region, a light that neither flickers nor fades, born of the same gravity that would extinguish everything else. In this calm persistence lies the paradox of TON 618, the most violent object in existence radiating with the stillness of a star frozen in eternity. From the corona and the surrounding magnetic fields of TON 618, powerful jets of matter emerge, narrow columns of plasma launched outward at speeds approaching that of light. These relativistic jets extend far beyond the host galaxy, cutting through intergalactic space for millions of light-years. They represent one of the most efficient ways the universe transfers energy from deep gravitational wells into the surrounding cosmos. The mechanism that forms them is rooted in the magnetic structure of space near the black hole. Rotating magnetic field lines anchored to the disk and twisted by the black hole's spin act as conduits through which charged particles are accelerated. As these fields wind up, they channel plasma along the poles, converting rotational energy into kinetic motion. The result is a continuous outflow, two opposing beams that pierce the darkness, visible only because of the radiation they emit as particles spiral within magnetic fields. The physics of such jets is complex but remarkably ordered. Near the base where the jet is born, the magnetic field dominates completely, guiding plasma in a tight column. The density is low, yet the energy density is enormous. As the jet travels outward, the surrounding medium provides resistance, shaping it into a narrow cylinder. Particles within the jet move in helical paths, producing synchrotron radiation that spans radio to X-ray wavelengths. Observations of other quasars show that these emissions flicker on timescales of years or decades, corresponding to variations in the flow near the core. For TON 618, the scale of its jets is so immense that any changes would unfold across millennia. To an observer on Earth, they would appear as steady, symmetrical extensions of light, fading only where distance and time blur them into invisibility. The energy contained within these jets rivals that of entire galaxies. They carry both matter and magnetic flux outward, depositing energy into the intergalactic medium. When they encounter denser clouds of gas, they form shocks that heat and ionize the surrounding material, creating bright radio lobes visible across enormous distances. These lobes mark the places where the jet slows and disperses, releasing its stored energy into the cosmic environment. Over time, they inflate giant cavities within the surrounding medium, sometimes hundreds of thousands of light-years wide. Such cavities persist long after the central engine quiets, serving as fossil imprints of the black hole's past activity. In the case of TON 618, these structures would be among the largest in existence relics of an era when the quasar's power was at its peak. The motion of matter within the jets is governed by relativity. The plasma accelerates until its velocity is so high that time for the particles slows relative to the outside universe. From a distant observer's perspective, the jet seems frozen in motion, its apparent speed affected by the angle at which it is viewed. When the jet points toward Earth, the light it emits appears boosted its brightness, amplified by relativistic beaming. For TON 618, the orientation is not precisely known, but even without perfect alignment, its luminosity is extraordinary, suggesting that both the mass of the black hole and the efficiency of its magnetic engine exceed typical values by wide margins. Along the length of the jets, magnetic fields maintain coherence across unimaginable scales. These fields twist and expand as they propagate, occasionally undergoing reconnection events that release bursts of energy. Such events generate flares of radiation visible as transient brightenings in distant radio observations. Over time, the jets entrain intergalactic material, mixing with ambient gas and slowing gradually until their energy dissipates. Yet even in their fading, they influence the environment, distributing heat and heavy elements that alter the chemistry of surrounding space. This process of feedback links the growth of black holes to the evolution of galaxies and clusters, ensuring that no system develops in isolation. TON 618's jets, operating over millions of years, would have played a defining role in shaping the thermal structure of the region it inhabits. At smaller scales, within a few hundred light-years of the black hole, the jets interact with the galaxy's own gas. Their passage clears cavities through the interstellar medium, compressing some clouds and dispersing others. The compression can trigger localized star formation, while the heat and pressure suppress it elsewhere. In this way, the jets act as both destructive and creative forces, erasing and seeding simultaneously. The energy they carry maintains a delicate equilibrium, preventing runaway cooling and collapse within the galaxy's core. In the case of TON 618, the balance achieved between inflow through the disk and outflow through the jets defines the entire life cycle of the host galaxy, keeping it stable through alternating periods of quasar activity and dormancy. The composition of the jets includes electrons, protons, and possibly heavier nuclei, all accelerated to near light speed. Within this, plasma shocks produce radiation across the electromagnetic spectrum. Radio telescopes detect the long wavelength emission from charged particles spiraling in magnetic fields, while X-ray and gamma-ray detectors capture the high-energy tail of the spectrum. The synchrotron process responsible for this radiation is remarkably efficient, converting kinetic energy into light with little loss. The resulting emission provides astronomers with one of the clearest signatures of relativistic motion in the universe. For TON 618, whose distance and brightness make it a reference point for extreme astrophysical processes, the detection of such radiation confirms the operation of these mechanisms on scales never before observed. Over cosmic time, the activity of the jets waxes and wanes. When the accretion rate drops, the magnetic fields weaken and the outflows fade. The lobes cool their radiation, shifting to longer wavelengths until they merge with the faint radio background. Yet traces remain elongated filaments of magnetized plasma stretching through intergalactic space relics of an age when the black hole fed voraciously. The persistence of these structures testifies to the durability of cosmic energy. Even as galaxies age and stars burn out, the signatures of long-past quasar activity endure faint but measurable across billions of years. In Ton 16's case, those echoes likely still exist, imprinted on the surrounding medium, like ripples frozen in the fabric of space. The jets also demonstrate the remarkable symmetry of natural law. The processes that generate them near stellar mass black holes within our galaxy follow the same equations as those at play in Ton 618, differing only in scale. Gravity, magnetism, and motion combine, universally producing patterns repeated from the smallest microquasar to the largest active galactic nucleus. This self-similarity reveals a deep coherence in the cosmos, one set of principles expressed across all magnitudes of energy and distance. Ton 618, by embodying the most extreme version of this pattern, allows researchers to test these laws where they approach their limits. When seen in the context of the universe's evolution, the jets of Ton 618 represent more than spectacle. They are conduits of transformation, redistributing matter and energy across intergalactic space. Their radiation influences the formation of new galaxies. Their magnetic fields shape the motion of cosmic plasma, and their existence bridges the smallest quantum interactions with the largest cosmic structures. Through them, energy from a single point deep within one galaxy becomes part of the universe's grand balance. In the silence of the void, these streams continue their outward journey, invisible to all but the most sensitive instruments, carrying the imprint of Ton 618's power into eternity. To distant observers, their light is soft and constant, a quiet reminder that even the most remote and unreachable corners of the cosmos remain connected by the steady work of gravity, magnetism, and time. Beyond the brilliant jets that pierce the galaxy's outskirts, the light surrounding Ton 618 bends and swirls in patterns shaped by gravity itself. This region, where light begins to curve rather than travel straight, marks the domain of the photon sphere, the boundary where photons can orbit the black hole in unstable circular paths. The photon sphere is not a physical surface but a threshold in space-time, a place where gravity is strong enough to trap light temporarily, before it either escapes outward or falls inward. For Ton 618, whose mass exceeds tens of billions of suns, this sphere would extend for billions of kilometers, encompassing a volume larger than entire solar systems. Within it, the ordinary geometry of space ceases to apply. Paths of light twist and loop, forming arcs and rings that would appear to an observer as luminous halos, distorted reflections of the disk and jets behind them. The effect is gravitational lensing, the warping of light by gravity, predicted by general relativity and confirmed through observation in countless systems across the cosmos. The bending of light near Ton 618 reveals the immense curvature of space-time caused by its mass. Any photon passing within a certain distance from the black hole's center follows a path dictated not by straight-line motion, but by the shape of the gravitational field. To an observer at great distance, this bending magnifies and distorts the view of whatever lies behind the black hole, creating multiple images or arcs. In extreme cases, light that travels around the black hole more than once can form a complete ring known as an Einstein ring. Though Ton 618 is far too distant for such detail to be resolved directly, simulations based on its properties allow astronomers to predict the visual appearance a central darkness surrounded by concentric arcs of light, each representing photons that have circled the black hole before escaping. These arcs would shimmer with the colors of the accretion disk compressed and intensified by gravitational blue shift. The gravitational lensing effect extends far beyond the immediate vicinity of the black hole. The entire galaxy of TON 618 acts as a lens bending light from background objects and distorting their shapes. Through this natural magnification, astronomers can study distant galaxies that would otherwise remain invisible. The principle applies universally. Massive objects deform space-time and light responds by following curved paths. In the case of TON 618, the strength of this lensing is extraordinary, capable of altering light trajectories across hundreds of thousands of light years. It demonstrates the seamless link between gravity and geometry, how mass not only attracts matter, but reshapes the very fabric through which light moves. Within the photon sphere, strange visual effects dominate. If one could hover just outside this region, the view of the universe would be profoundly altered. Light from behind the observer would wrap around, forming an image of the back of one's own head, as photons make partial orbits before returning. The disk below would appear duplicated and inverted, its far side mirrored around the circular boundary of the black hole's shadow. The region directly ahead would appear dark, not because light is absent, but because every path leading inward terminates at the event horizon. For TON 618, this shadow would span thousands of astronomical units, a perfectly circular silhouette framed by a glowing ring. The symmetry of this feature, preserved even under rotation and distortion, represents one of the clearest visual signatures of a black hole. The phenomenon of gravitational redshift becomes dominant here. As light struggles to climb out of the gravitational well, its wavelength stretches, losing energy and shifting toward the red end of the spectrum. To distant observers, radiation from near the photon sphere appears dimmer and redder than it was when emitted. Conversely, light moving inward toward the black hole is blue-shifted, gaining energy as it falls. This constant exchange of energy between light and gravity defines the behavior of photons in curved space-time. For TON 618, the gradient of this effect is extreme, with measurable changes in wavelength, even across relatively small distances near the event horizon. The bending of light around the black hole also causes time to behave differently for observers in various locations. To someone far away, events near the photon sphere appear slowed, as if unfolding in slow motion. A pulse of light emitted near the event horizon takes longer to reach the observer, stretched by the same curvature that bends its path. In contrast, for matter within the gravitational field, time proceeds normally. This difference, known as gravitational time dilation, is not an illusion, but a measurable effect, one that demonstrates the relativity of time itself. In TON 618, the degree of time dilation is immense. A few minutes near the photon sphere could correspond to centuries in the outer universe. Yet despite this distortion, the system maintains equilibrium with light motion and gravity interlocked in perfect mathematical precision. The lensing produced by TON 618 extends its influence beyond aesthetics. It provides a natural laboratory for testing the laws of physics under conditions impossible to replicate elsewhere. By studying how light from background sources bends around such quasars, scientists can measure the mass distribution of both the black hole and its host galaxy. They can also test alternative theories of gravity, seeking deviations from Einstein's predictions. So far, observations have shown remarkable consistency with general relativity, even when applied to systems of this magnitude. The alignment between theory and observation reinforces the universality of the laws that govern spacetime, from the orbits of planets to the light of the most distant quasars. The photon sphere also defines the outer boundary of the black hole's influence on light. Beyond it, photons can escape to infinity. Within it, their fates are sealed. Some spiral inward, crossing the event horizon, while others linger briefly in unstable orbits before being scattered outward. The brightness of the ring that marks this boundary depends on the viewing angle and the spin of the black hole. For rapidly rotating black holes like TON 618, the ring would appear slightly flattened on one side, a subtle signature of rotation that encodes information about angular momentum. Detecting such features in other nearer systems has allowed astronomers to infer spin rates, and TON 618's enormous energy output suggests that it too spins at a significant fraction of the speed of light. Gravitational lensing around TON 618 transforms not only light, but also our understanding of perspective. It shows that what we perceive as straight lines and uniform motion are on cosmic scales illusions shaped by curvature. Every photon that leaves the vicinity of the black hole carries the record of its journey through warped space encoded in its direction, wavelength, and delay. When this light finally reaches Earth, it allows observers to reconstruct the geometry of a place billions of light-years away. In this sense, TON 618 acts as both an object and an instrument, a cosmic mirror that reveals the structure of space-time through its distortions. The photon sphere stands as a threshold between visibility and concealment, between light that escapes and light forever lost. It is the stage upon which the drama of gravity reaches its visual climax, where matter, energy, and geometry converge in silent symmetry. Around TON 618, this boundary glows softly against the blackness, marking the place where light hesitates on its final choice, whether to flee into space or to vanish into the darkness from which no signal returns. The calm persistence of this boundary, constant across eons, reflects the enduring balance of nature's most fundamental forces, still unfolding unchanged within the heart of the largest known black hole in the universe. Beyond the photon sphere lies the most mysterious frontier of TON 618, the event horizon, the surface of no return where the escape velocity equals the speed of light. It is not a material boundary, but a limit in space-time marking the transition between regions where light can escape and where it cannot. For a black hole of this magnitude, the event horizon spans a circumference larger than the orbit of Neptune around the Sun, a sphere of gravity so immense that it distorts the shape of time and space around it. Within this invisible boundary, every path curves inward, and all trajectories lead to a single fate, the central singularity. Yet to a distant observer, nothing ever seems to cross the horizon. Matter falling toward it appears to slow its light stretched into redder and fainter tones until it fades completely frozen at the edge by the effects of time dilation. This illusion, a consequence of relativity, ensures that the event horizon remains perfectly still, to all external observation, an eternal silence suspended in the fabric of the universe. The formation of such a horizon is the natural outcome of gravitational collapse. When a sufficiently massive body exhausts its internal energy sources, no known force can resist its inward pull. The matter compresses beyond the limits of atomic structure, shrinking until density and curvature reach extremes where the equations of general relativity predict a singularity, a point where space-time itself terminates. Around this singularity, the event horizon forms as a boundary, separating the observable universe from the unobservable interior. For TON 618, this process occurred billions of years ago, built upon generations of smaller collapses, mergers, and accretions. The result is a gravitational entity so vast that its influence extends across intergalactic distances, shaping the motion of stars and gas within its galaxy, and altering the behavior of light itself. Near the event horizon, gravity's pull warps both space and time to such an extent that all processes slow dramatically when viewed from afar. A photon emitted just above the horizon takes longer to escape its energy diminished as it climbs through the curved space-time. This gravitational redshift renders the region nearly invisible. Even in wavelengths capable of penetrating gas and dust, the black hole itself remains dark. What is seen instead is the light from the surrounding accretion disk distorted into a ring around the shadow. For TON 618, that shadow would appear vast, encompassing a region many times wider than the orbit of Pluto, yet perfectly circular due to the immense symmetry of the gravitational field. Within the shadow, no light emerges, only the faint suggestion of its boundary, where radiation skims the edge of the abyss before being drawn inward forever. The concept of time dilation reaches its greatest expression here. An object approaching the event horizon never appears to arrive. Its signals slow and fade, stretched across eternity. To the falling object itself, time continues normally, and the crossing occurs in an instant. This duality of experience, frozen from without, continuous from within, defines the horizon's paradoxical nature. For TON 618, whose mass produces curvature on a cosmic scale, the time dilation is extreme. If a spacecraft were to approach its horizon, hours for those on board could correspond to millions of years for the outside universe. The distinction between moments and epochs dissolves at the edge of this gravitational well, where time and distance cease to behave independently. The physics governing this region also dictate that nothing, not even information, can escape from within. Once matter crosses the horizon, it becomes part of the black hole's mass, contributing to its total gravity, but revealing nothing of its previous state. This principle gives rise to one of the central mysteries in modern physics, the information paradox. According to quantum theory, information cannot be destroyed, yet classical relativity allows no path for it to leave the black hole. The reconciliation of these ideas remains an open question, one that systems like TON 618 help to constrain by providing natural laboratories for studying the interaction of quantum mechanics and gravity at their most extreme. Some theories propose that information is encoded in subtle variations on the event horizon itself, forming a holographic record of everything that has fallen in. If true, TON 618's horizon would contain an unimaginably vast amount of encoded data, an archive of its entire cosmic history written into space-time at the smallest possible scale. The temperature associated with a black hole predicted by theoretical physics is inversely proportional to its mass. For smaller black holes, this temperature allows a faint emission of radiation known as Hawking radiation, but for a black hole as massive as TON 618, the temperature is effectively zero. Its evaporation timescale exceeds the age of the universe by orders of magnitude. It does not radiate, it only absorbs. The horizon, though conceptually active, remains perfectly stable, impervious to any external influence short of another black hole collision. It stands as the ultimate absorber, a one-way surface that grows imperceptibly each time it consumes matter or light. Over billions of years, this gradual accumulation has increased TON 618's mass to its present colossal value, making it the most extreme gravitational object yet identified. The environment immediately outside the event horizon is dynamic. Magnetic fields twist plasma races along curved paths, and energy is released as particles accelerate toward their end. Some of these particles, guided by magnetic lines, escape as part of the jets described earlier, while others spiral inward, releasing their final radiation just before crossing. This last light emitted from the inner edge of the disk forms the luminous ring that defines the quasar's brilliance. In TON 618, that glow persists, because the inflow of material is continuous. As older matter disappears, new gas arrives from the surrounding galaxy. The result is a perpetual balance between feeding and fading, between appearance and disappearance. To imagine standing near the event horizon is to consider the breakdown of all familiar reference points. Directions lose meaning, distances distort, and the difference between motion and stillness vanishes. The curvature of space-time is so extreme that all paths converge inward. The very concept of rest ceases to apply because every object, regardless of its velocity, moves toward the singularity once it crosses the threshold. Yet despite this inevitability, the horizon is perfectly featureless, described entirely by just a few parameters: mass, spin, and charge. This simplicity encapsulated in the no-hair theorem means that ton 618, despite its enormity, can be fully defined by only two measurable quantities: its mass and rotation, since astrophysical black holes carry negligible charge. Everything else that once fell in every star cloud or particle is reduced to these abstract characteristics. The event horizon of ton 618 is therefore both a boundary and a beginning. It marks the end of observable space and the start of a region governed by equations that defy direct confirmation. Yet its influence extends far beyond its invisible surface. The gravity that binds galaxies, the light that bends through space-time, and the radiation that illuminates the universe all bear its signature. Within that darkness lies the purest expression of relativity, an unchanging example of how mass and space interact to create structure and silence. If one could watch from afar, the horizon would seem eternally calm, unmoving, and complete a smooth black surface encircled by fire, perfectly still against the drift of cosmic time. And in that stillness, ton 618 continues its quiet work, shaping the universe around it with the steady gravity of absolute permanence. Inside the event horizon of ton 618, all familiar frameworks collapse into abstraction. No signals escape, no light returns, and no observation can reveal what unfolds beyond that invisible surface. The region is defined entirely by theory, not by direct measurement. According to the equations of general relativity, once matter crosses the horizon, it follows space-time trajectories that converge inevitably at the singularity, a point where curvature becomes infinite and known physics loses coherence. There the separation between space and time ceases to exist. All directions lead inward, and the distinction between past and future becomes meaningless. For ton 618, with a mass of tens of billions of suns, this singularity would not resemble a single point in space, but a ring-like structure if the black hole possesses significant spin. In that configuration, space wraps around itself, forming a rotating funnel, where matter is compressed into densities beyond any conceivable limit. Whether this singularity is a literal point or a domain where quantum gravity takes over remains uncertain. It is the boundary of human knowledge where mathematics extends beyond direct experience. Within the horizon, the inward journey of matter proceeds unopposed. There is no solid core to strike, no surface to rest upon. The gravitational pull is so complete that space itself flows inward faster than light can travel outward. To any particle or photon, motion toward the center becomes inevitable. The geometry of space-time carries everything along as if the entire universe were collapsing into a single direction. Time, as measured by anything within, continues normally. The experience of falling feels finite, yet from the outside this fall appears frozen at the edge, never completed. This dual perspective, simultaneous completion and eternal delay, is an intrinsic property of the relativistic horizon. Ton 618 magnifies it on a scale that transcends ordinary intuition, extending these effects across distances larger than entire planetary systems. The singularity at the center, as predicted by classical theory, represents infinite density and zero volume. But such infinities signal the breakdown of the equations themselves, not necessarily a physical reality. Many physicists believe that quantum effects must intervene, creating a new description, where space-time cannot compress indefinitely. In this view, the singularity might be replaced by a region of extreme but finite density, governed by principles not yet unified in existing theories. Some approaches suggest that space-time becomes quantized, structured in discrete units rather than continuous curves. Others propose that information is preserved in quantum correlations along the horizon, preventing total erasure. Yet none of these possibilities can be tested directly, leaving the interior of TON 618 as a silent hypothesis, an unseeable truth that anchors the observable universe. The interior's structure also depends on rotation. If TON 618 spins rapidly, its event horizon flattens slightly, and the singularity becomes a ring encircled by an inner region of warped space-time known as the ergosphere. Within this zone, space itself rotates with the black hole, dragging all matter and light along in its motion. The ergosphere allows for the extraction of energy through processes such as the Penrose mechanism, in which particles split, one falling inward and the other escaping with greater energy than before. Though this process is theoretical, it offers a possible explanation for how rotating black holes power the colossal jets observed in quasars. For TON 618, the sheer scale ensures that such phenomena occur on cosmic dimensions, transferring a fraction of its rotational energy to the magnetic fields that launch plasma into space. This coupling between spin and energy release demonstrates that even within the boundaries of darkness, dynamic interactions continue unseen but persistent. The region beyond the singularity remains purely speculative. Classical solutions to Einstein's equations allow for mathematical continuations of space-time that pass through the singularity into other regions, sometimes described as white holes or alternate universes. In these solutions, matter entering one side might emerge elsewhere transformed but conserved. Yet these interpretations face fundamental issues of stability and causality. Any perturbation in real physics would likely destroy such pathways before they could exist. For TON 618, the conditions are so extreme that no meaningful extension can be described. The singularity marks an absolute termination, a limit of description beyond which even theoretical continuation loses physical relevance. The laws of nature, so reliable everywhere else, end here not in contradiction but in incompleteness. Despite its invisibility, the interior of TON 618 exerts a profound influence on the universe beyond. The mass of everything that has fallen in determines the curvature of space-time outside, fixing the gravitational field that shapes the motion of stars, gas and light. The singularity itself remains hidden, yet its existence is encoded in the behavior of everything surrounding it. The orbits of stars in the host galaxy's core, the temperature of the accretion disk and the bending of a light around the horizon all depend on the exact mass concentrated within. Thus, the unseen interior defines the visible universe, its silence determining the music of motion that echoes across space. From a philosophical standpoint, the region inside TON 618 represents the end of physical meaning, not because it violates law, but because it isolates information completely. No observer can cross the horizon and return to report. The interior exists as a necessary solution of the equations, not as an accessible realm. This distinction gives black holes their unique role in cosmology. They are not objects within space, but regions where space itself terminates. TON 618 magnifies this reality until it becomes almost abstract, a single point of infinite compression, embedded within a galaxy of 1 trillion stars itself, one node within the cosmic web. Its presence affirms both the reach and the limitation of human understanding. Some theories of quantum gravity propose that the singularity might not destroy information but transform it. In this framework, the event horizon functions as a membrane recording the quantum state of everything that crosses. Over inconceivably long timescales, this information could be re-emitted through subtle radiation, preserving the continuity of cause and effect. For stellar mass black holes, such radiation might eventually lead to evaporation, but for TON 618 the timescales exceed 10 to the power of 100 years, so vast that they transcend the lifetime of all stars and galaxies. For practical purposes, it is eternal, a monument of gravity that will persist long after the universe has grown dark and cold. Within the boundary, matter continues its silent fall. Atomic structure dissolves, particles merge, and forces unify. Space folds inward upon itself until geometry ceases to have meaning. The distinction between object and field disappears, leaving only the curvature that defines existence. The interior is not chaos, but perfect order, an inevitable outcome of the laws that created it. TON 618 thus stands as both a beginning and an end, a point, where the universe contemplates its own structure through gravity's purest expression. It is the natural consequence of evolution, on the largest scale where accumulation and collapse meet in timeless equilibrium. Though the singularity cannot be seen, its effects will outlast everything visible. Long after galaxies drift apart and stars fade, TON 618 will remain invisible, but immense, holding within it the record of an ancient universe. It will persist as the final architecture of existence, a silent, indestructible form born of time, mass, and gravity. In that permanence lies both mystery and resolution, a place where knowledge halts, where the universe folds inward, and where the calm of absolute darkness becomes the most enduring structure of all. Though the interior of TON 618 lies forever beyond observation, the effects of its mass ripple outward through every surrounding layer of space-time. The black hole's gravity influences not only the motion of stars and gas in its host galaxy, but also the passage of time itself in regions far beyond its horizon. In the vicinity of such an immense object, clocks tick more slowly, light shifts toward longer wavelengths, and even the geometry of empty space becomes curved. This phenomenon, known as gravitational time dilation, is not confined to the immediate horizon, but extends through the galaxy's core, decreasing in strength with distance. In this way, the very rhythm of time around TON 618 differs from that of the wider universe. Seconds near the center correspond to hours or years in regions farther away. To observers within the host galaxy, these differences are imperceptible, but to astronomers across billions of light years, they manifest as the slow, red-tinged glow characteristic of massive quasars. Time dilation arises naturally from Einstein's general theory of relativity, which links gravity to the curvature of space-time. In the presence of enormous mass, space is compressed and time stretched. The effect is symmetrical. As light climbs out of a gravitational well, its frequency decreases, and as it falls inward, its frequency increases. In TON 618's environment, this interplay between redshift and blueshift shapes the appearance of the entire system. Radiation emitted from the inner accretion disk loses energy as it escapes, appearing redder to distant observers, while light from material falling inward gains energy, appearing bluer locally. These shifts create gradients across the disk's face that encode the black hole's rotation mass and energy output. Each photon carries not only light but a record of how time and gravity intertwine. Near the photon sphere, where light orbits briefly before escaping, time dilation becomes extreme. To an external observer, processes occurring there appear to unfold thousands of times more slowly than those in ordinary space. A single rotation of gas around the inner disk might last only minutes locally, but seem to take centuries when viewed from afar. For TON 618 with its immense mass, this disparity stretches even further. The geometry of time around it forms concentric shells of slowing rhythm, each layer ticking fractionally slower than the one before, until motion itself seems to pause at the horizon. Yet the laws governing these transitions remain perfectly smooth. No discontinuity separates one state from another. Space and time adjust continuously to the presence of gravity, maintaining equilibrium even under such distortion. This slowing of time has measurable consequences for the quasar's radiation. The energy emitted from regions close to the event horizon is both redshifted and delayed. As a result, variability in brightness that might occur within the inner disk is smoothed out by the time it reaches observers billions of light-years away. The apparent steadiness of TON 618's light is therefore not only a function of scale, but also of relativity. Each fluctuation is stretched in time, its rise and fall dispersed across vast intervals. What appears constant is in reality a sequence of changes too gradual to perceive. In this sense, the black hole transforms motion into stillness, converting the dynamics of matter into the calm persistence of light. Time dilation also affects the paths of particles escaping along the jets. As they move outward through regions of differing gravitational potential, their clocks accelerate relative to the black holes. From the perspective of the distant universe, these particles seem to maintain their brightness and coherence far longer than they would otherwise. The extended visibility of quasar jets across millions of light-years owes much to this relativistic stretching of time. Each photon emitted along their length carries the combined imprint of motion, energy and delay, linking the heart of TON 618 to the distant edges of the cosmos. The measurement of such effects allows astronomers to determine the black hole's properties with remarkable precision. By analysing the redshift of spectral lines, the width of emission features and the time delays between different wavelengths, they reconstruct the geometry of space-time surrounding the horizon. In TON 618, these measurements reveal the signatures of both immense mass and significant spin. The rotation stretches the horizon into an oblate shape, drawing space-time around with it in a phenomenon called frame dragging. Within this zone, even light must rotate with the black hole unable to remain stationary. The frame dragging effect blends with time dilation to create a region where the distinction between space and time becomes fluid, where motion through one inevitably entails motion through the other. The interplay of these effects shapes the quasar's spectrum. Light emitted from material moving toward the observer is blue-shifted and amplified, while light from receding material is red-shifted and diminished. The result is an asymmetric brightness across the disk's face, one side appearing slightly brighter than the other. In smaller black holes, this difference can vary quickly, producing flickering light curves. For TON 618, the change is glacial, unfolding over centuries, rendering its appearance tranquil and steady. Every fluctuation of energy is stretched by the immense gravity, its rhythm transformed into a slow, unbroken hum that fills the surrounding universe. Time dilation is not limited to the immediate vicinity of the black hole, but influences the perception of its entire environment. The light from TON 618 takes more than 10 billion years to reach Earth, and in that time the universe itself expands further, stretching the wavelengths of radiation. This cosmological redshift combines with gravitational redshift to shift the quasar's spectrum deep into the infrared. The photons arriving now began their journey when the universe was less than half its current age, carrying within them a record of ancient space-time. In a sense, to observe TON 618 is to look backward, not only across distance but through layers of slowed time, each photon a messenger from a region where moments pass more slowly, and where the concept of duration differs fundamentally from our own. For the black hole itself, time has no universal meaning. The singularity experiences its evolution in an instant, while the universe outside experiences it as eternity. In relativity, this contradiction is resolved not through paradox but through geometry. Time does not flow the same for all observers. It stretches and folds according to mass and motion. Around TON 618, space-time forms an immense basin in this cosmic fabric, a curvature so deep that even time's direction becomes uncertain near the horizon. The equations describing this curvature predict every observed phenomenon: the bending of light, the redshifting of radiation, the apparent stillness of accretion, and the symmetry of the shadow. All arise naturally from the relationship between gravity and time. Beyond its physical implications, the dilation of time around TON 618 redefines the scale of cosmic endurance. Events that would seem fleeting on smaller scales, fluctuations in luminosity interactions between gas clouds, changes in spin unfold here over spans that rival the lifetimes of galaxies. The black hole turns rapid processes into geological epochs stretching seconds into millennia, and millennia into stillness. Its existence reveals a universe where time is not fixed but malleable, expanding and contracting in response to gravity's quiet command. Around TON 6 and 18, the very pace of reality slows until motion and rest become indistinguishable, a continuous equilibrium where light, space and time converge in unending calm. Having journeyed from the outermost filaments of the cosmic web to the heart of TON 618's gravity, one reaches now the inner edge of understanding, a place where the measurable and the imaginable meet. Around this black hole, every physical process from the orbit of distant stars to the flicker of high-energy radiation follows the same laws that govern the smallest particles unified by gravity's command. Yet the scale of TON 618 transforms those laws into something almost abstract, stretching them across distances and durations that defy human perception. Here light becomes an instrument of geometry, time becomes elastic, and energy itself takes on the role of storyteller, carrying records of events billions of years old. To look upon TON 618 is to confront a truth both simple and infinite, that the universe in all its complexity obeys patterns that remain consistent from atom to galaxy, from moment to eon. The measurable properties of TON 618, its mass, luminosity, distance and structure, converge to form a portrait of balance. Gravity pulls inward with irresistible strength, yet radiation, magnetic pressure and rotation create outward forces that prevent collapse into chaos. The result is not disorder, but order of the most profound kind, a system stable enough to endure for billions of years, luminous enough to be seen across half the observable universe, and yet governed by equations that fit within a few lines of mathematics. Its vastness is matched only by its simplicity. Every photon leaving its accretion disk, every particle accelerated along its jets follows trajectories predicted precisely by general relativity and plasma dynamics. Nothing within it violates the laws of physics, though nearly everything within it pushes those laws to their limits. The stability of such an immense system depends on equilibrium maintained over cosmic time. Matter flows inward from the galaxy's outskirts in steady currents, while energy flows outward through radiation and jets. The two processes balance perfectly, ensuring that the black hole grows slowly, even as it shines with astonishing power. In TON 618, this balance is amplified to extremes. Each second it may convert the equivalent of several suns' worth of mass into light, yet the total supply of available matter ensures that this rate can continue for tens of millions of years without exhaustion. The quasar phase is therefore not an outburst but a long sustained breath, a steady exhalation of energy across the ages. The calmness of this radiation spread across all wavelengths explains why the light that reaches Earth appears constant and serene. Over human lifetimes, TON 618 does not flicker, it simply endures. In the surrounding galaxy, this quiet power shapes evolution. The radiation from the core heats the interstellar gas, preventing it from collapsing into new stars too quickly. At the same time, the jets distribute heavy elements into the halo-enriching regions that would otherwise remain chemically simple. Through these mechanisms, TON 618 exerts a form of regulation over its environment, guiding the pace at which the galaxy changes. The black hole is not a destroyer, but a moderator maintaining stability by balancing extremes of creation and destruction. This feedback loop is seen throughout the universe wherever massive black holes reside, but in TON 618 the effect is magnified by scale-extending influence beyond the host galaxy and into intergalactic space. On the grandest level, TON 618 participates in the same cosmic web from which it arose. The energy it releases, though small compared to the universe as a whole, contributes to the heating of intergalactic gas, affecting how future galaxies will form. Photons emitted during its quasar phase will travel forever, their wavelengths stretching as the universe expands, becoming part of the diffuse background that fills space. In this sense, TON 618 is both product and contributor to cosmic evolution, an outcome of gravity's work and a source of new order that shapes what follows. Every stage of its life connects outward from the infall of gas through the emission of light, from the smallest atomic transitions to the structure of the universe itself. Even across billions of years, the presence of TON 618 will remain. When the quasar eventually dims and the inflow of matter subsides, the black hole will persist as a silent remnant at the galaxy's core. Its mass will continue to curve space-time, binding the stars that survive around it and defining their orbits. As the galaxy ages and its light fades, TON 618 will remain invisible yet dominant, its gravity holding what is left together. Over longer spans still, when star formation ceases throughout the universe and galaxies drift apart, it will continue to exist, one of countless black holes, forming the last enduring architecture of the cosmos. Even in a distant future when expansion outpaces all interaction, TON 618 will remain slowly absorbing stray matter, maintaining its horizon as the ultimate stillness. The enduring nature of such an object redefines what permanence means. Everything visible in the universe, stars, planets, and even galaxies, will eventually change, fade, or dissolve. Only black holes, and particularly the most massive among them, persist on timescales approaching infinity. TON 618 thus represents not just a chapter in cosmic history, but its conclusion, the form into which matter ultimately settles when energy has been radiated away. The same processes that power the quasar today will one day cease, yet the structure they sustain will remain. In that continuity lies the quiet symmetry of creation and decay, each feeding the other, neither absolute, both expressions of the same physical law. For observers on Earth, TON 618 serves as both a window and a mirror. It reveals the distant past of the universe while reflecting the underlying unity of nature. The light that arrives now began its journey when the Milky Way was young and simple, long before life arose on this planet. That light carries information about the early cosmos, about the density of matter, the composition of gas, and the shape of space-time itself. By studying it, astronomers reconstruct the history of cosmic evolution, tracing how small fluctuations in density grew into galaxies and clusters. TON 618 in this role becomes an anchor in deep time, linking what is seen today to what existed when the universe was less than half its current age. The scale of such distances defies imagination, yet the principles behind them remain accessible. Light travels at a fixed speed, gravity curves space in predictable ways, and the equations that describe them hold true from laboratory experiments to quasars at the edge of the observable universe. This consistency is what makes TON 618 meaningful beyond its size. It demonstrates that the same physics governing the orbit of a planet applies to phenomena spanning billions of light years. Its immensity does not make it exotic, but exemplary, a clear and magnified instance of universal law. In its behavior, simplicity and grandeur converge, reminding us that the cosmos is not chaotic, but ordered, vast, yet comprehensible. Eventually, the light from TON 618 will fade as expansion stretches it beyond detection. The photons now leaving its accretion disk will in untold eons become part of the cosmic microwave background, indistinguishable from the faint heat of creation itself. Yet the record they carry will endure in theory and in memory, a reminder that within the stillness of space energy once flowed with quiet precision from the heart of the largest black hole known. Its influence will persist not through sound or motion, but through the subtle imprint it leaves on the structure of space-time. Even as time expands towards silence, that curvature will remain invisible but exact, the last trace of the quasar's radiance. Thus the journey inward comes full circle, from the vast cosmic web that gave birth to galaxies to the elliptical host that formed around ancient mergers to the quasar that blazed at its heart. Every stage of TON 618's existence fits seamlessly into the unfolding of the universe. It is not an anomaly, but a culmination, an inevitable expression of cosmic law. Through it, one can glimpse both the fragility of light and the permanence of gravity, both the motion of matter and the stillness of time. TON 618 endures as a symbol of the universe's quiet symmetry, a single point where all forces meet balanced eternally between radiance and darkness.